All right, in this lecture we are going to talk about differentiable manifolds. And differentiable manifolds are an extension of topological manifolds. All differentiable manifolds are topological manifolds, and by the way, all topological manifolds are topological spaces. But not all topological manifolds are differentiable manifolds, and we need to understand exactly what the distinction is. And we begin with the basic canonical picture of a topological manifold, which is a topological space X with its topology and an atlas. And remember that atlas is the set of charts on the topological space, and these charts have a chart region. The chart region would be something like U1 and perhaps U2, and then perhaps let me do a better one there, then perhaps U3, and the gammas are these homeomorphic maps that take us to Euclidean space, RD. And RD, remember, is shorthand for R cross R D times. And that is the set of all ordered D tuples, A, B, etc., 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 right, where there's D entries. So these maps gamma are homeomorphic maps, which means that they go in both directions. They're continuous in both directions. Gamma I is continuous and gamma I inverse is continuous. Well, I guess in this case it's gamma 1. The way I've drawn it here is gamma 1. And likewise, each chart region has its own map. So gamma 2 and gamma 2 inverse goes to a different RD. I erect these little things here like this because I'm trying to evoke a sense of Euclidean space with two dimensions, but of course RD is in D dimensions. But all of these homeomorphic maps between the chart region and RD all go to the same dimensional region. All of these charts cover the entire topological space, and that forms your atlas. And locally, each chart region is locally homeomorphic to some region of Euclidean space. In fact, I should indicate that. It's locally homeomorphic to a region. And that region, in this case, would be gamma 1 U1. And over here, that region would be gamma 2 U2, like that. And what these gammas mean is the gammas are essentially going to be our way of converting all the activity that goes on in our topological space into something that's happening in Euclidean space. And we can do calculus here. We can do multivariable calculus here, and because we can do multivariable calculus here, we can solve all kinds of math problems. And presumably, we come up with laws of physics that we can study here, and by using these chart functions, it tells us what's going on here. In some ways, you can think of this as the real world. There's a little bit of philosophy of science here that I do not want to get into because I'm not really qualified to discuss it much. This is the real world, or perhaps you might want to call this is our model of the real world. But regardless of whether this is the real world or the model of the real world, this is definitely a model of the real world, right? And we can operate on this model and find out about this model. Or if we say this is the real world, we're using this as the model and this is reality. And these chart maps are a way from going from the reality to the model or the model to the model, depending on how you want to look at this. Regardless, this is where we do all of our work. And this is where all of our labor studying math is as a physics student. This is where it's done. So with that in mind, it is important to understand that the result of this map, gamma 1 of, say, a point P, let me do this for a specific point now, a point P, and that will map through gamma 1 to a point here called gamma P, gamma 1 of P. Gamma 1 of a point P is an ordered n tuple. I'll call it alpha 1, alpha 2, or actually an ordered d tuple, right, because it's going to a d-dimensional manifold. So gamma 1 is a large d tuple, and that d tuple is called the coordinates of P. And the coordinates only make sense in the context of a chart. And that's one particular chart here, U1. U2 is a totally different chart, and the points inside there have its own coordinates, and their coordinates are actually in a different space. It's important to think of this as a different Euclidean space altogether. It's not just like in a different part of the same Euclidean space, it's in a different space altogether. And this open region is homeomorphically mapped to this open region, and they're given different d-tuples. This map is totally different, and the coordinates are totally different. Now, everything we've described here is exactly what we learned last time. This is all true for a topological manifold. The question is, what do we need to make it a differentiable manifold? All right, but right now I'm going to hide differentiable because it's really only a topological manifold. All this stuff exists in a topological manifold. In order to understand a differentiable manifold, we have to first study something called transition functions. And transition functions are going to be maps, when they're appropriate, from here to here. And that's what we're going to turn to now. We're going to turn to the notion of transition functions. So I'm going to draw a very canonical diagram. When I say canonical, what I mean is you'll see it in almost every darn book on the subject you ever pick up. If you ever pick up a book about differential manifolds, you will see this diagram. U1, U2, U1, 2. U1, 2 is U1 intersection U2. These are two charts. The atlas A consists of U1, gamma 1, U2, gamma 2, and a whole bunch of other charts, say. These are only two charts. So this atlas covers some topological space. In fact, the topological space will be X, Tx, and it'll have its atlas A. And this atlas has a lot of charts, but we're going to just look at two of them. The two charts we're looking at have an intersection. And as we've already seen in the stereographic projection, charts frequently have intersections, and sometimes they're very, very severe. You may remember in the stereographic projection, when we looked at the sphere without the point and the line, there were two charts. One chart was all in black. One chart was all the points except for the North Pole. The other chart were all the same points except for the South Pole and including the North Pole. So these two charts overlap entirely. There's only one point of distinction between the two charts, meaning U2 is all of U1 except for one point and adding a new point, and vice versa. So the idea of charts overlapping is the norm. It's actually the norm. Charts will overlap. Now you can design systems that actually the charts overlap a lot less severely. For example, if your topological space was, say, a circle, you might make a chart for here and a chart for here and a chart for here, and then you might make another chart for here, for here, then for here, and then for here, like that. So you have the green charts are this one, and this one, and they certainly overlap the red charts, but the overlap is not as severe, right? So that's my point, is you don't have to have severe overlaps. I don't want you to read too much into the stereographic projection example, but you can have overlaps, and you must have overlaps. The reason you have to have overlaps is because and you can think about this, you have, these are open sets. These neighborhoods are open sets. And in order to cover the space, these open sets are going to have to overlap. And the reason, of course, is because if they don't overlap, the boundaries of the open sets are not going to be included, and the boundaries of the open sets are part of the topological space. So you've got to get these open set boundaries in, so they have to overlap, basically. So there's going to probably, in this circumstance, for example, there's going to be other open sets out there that are going to be overlapping as well, because no boundary, all these boundaries are going to have to ultimately be covered by multiple open sets. But we're only going to look at two. We're only going to look at two, right? See if I can undo all this dotting here. It's a lot of tapping. I hope it's not too annoying. Okay, so now, so this is a canonical picture, except I got to finish it. This will be gamma 2 is that map, and this map is gamma 1, and this goes to some region in RD, and this goes to some region in a different RD. And of course, when I talk about RD, I'm talking about RD with its topology, and that's the topology of the open ball, right? And the reason is that's the topology we know that we can do all our calculus in, right? When we learned calculus, we didn't learn that, oh, you need a topology in the plane or in three-dimensional space that involves the open balls. But we do, and the closest thing we ever got to it, if you even did it, because many calculus courses don't do it, is the epsilon delta proofs about limits, right? Where you're looking for deviations in the range inside delta, given deviations in the domain inside epsilon. This is basically the open ball topology at work for a metric space. So you can create distances, so you can create the diameter of balls and all of that. And all of that exists in the usual topology of RD. It's just generalized to slightly higher dimensions. So when I talk about its mapping to Euclidean space, I'm talking about Euclidean space with this usual topology. Because Euclidean space, I think it only means RD cross RD, etc. So it's only these D-tuples. And the D-tuples is part of it, but without the topology of the open balls, the D-tuples don't mean much, right? There's no way of separating them, for example. Okay, so we've mapped to the topology, we've mapped to the, we've got these maps going. Now we're going to look at this one unique point P. Well, we're going to look at P. It's not particularly unique. It lives inside this intersection. It lives inside of U12. So P is an element of U12. And the nice thing for P is that it can be mapped into these regions. It can be mapped to gamma 2P, which might be here, and it can be mapped to gamma 1P, which might be there. And what's important about that is that every point inside U12 can be so mapped, and ultimately every point inside U12 will map to some subregion of the overall image of U2. Likewise, every point of U12 will be mapped to the image of region U12 under the mapping U1. Now, if U12, I'm going to cross-hatch it in red here, notice that U12 here is a simply connected space. Simply connected, we defined it in our last lecture, but we defined, or in one of our previous lectures, but it's also a connected space. Let's not worry about it being simply connected. It's just a connected space. These are homeomorphisms, right? These are homeomorphisms, meaning that they're one-to-one, they're on-to, which is also called surjective. They're surjective, and they're bicontinuous. Bicontinuous. And because of that, they are homeomorphisms. And as such, they will preserve topological properties, including connectedness. So if this is connected here, this is going to be connected here. Furthermore, you're not going to develop any holes in here like that, because if you're simple connectedness, which means there's no holes, is a loose definition of what simple connectedness means. If you're simply connected, that's a topological property too, and they're preserved. Therefore, it's preserved by homeomorphism. So you're going to have these two regions, just like this, and the point P is going to have an image in both regions, as is every point in U12. So now our question becomes, I want to make a map from here to here. I want to make a map from RD to RD, right? Right now, these maps are, the important thing about these maps is that they are from X, U2 specifically. They're actually not really from X. You would have to write gamma 2, you'd have to write gamma 2 is a map from U2, which is a subset of X, to RD, to be very precise. Because gamma 2 doesn't work for the points in U1. It works for the points in U2. It only works for the points in U1 that are also in U2. And likewise for all of the other charts, right? So that's why it's very chart specific. And when I say chart, I'm talking about the region and the map, right? The region and the map together are a chart. So I could call this the chart region, but sometimes I'll call that just the chart if I slip up. Okay, so we're now looking for a map from RD to RD though, right? And that's good because if we had a map like this, it's multivariable calculus, right? It's just ordered d-tuples to ordered d-tuples. We can do multivariable calculus on a map like that. So how do we build that map? Well, it's actually pretty obvious, right? I just take the point P, well, and I guess I'll go back to red. I don't know why I'm, well, green, I guess is appropriate. I think my color coding is not very disciplined here, but gamma 1 inverse, right? I'm going to this point, right? I'm taking this point. This point is gamma 1p. So gamma 1 inverse of gamma 1p, which also looks a little bit ridiculous, right? Gamma 1 inverse of gamma 1p is obviously p, right? Well, I want to get up here, so I just use gamma 2 on that. Gamma 2. So I'm taking the function gamma 2, the mapping gamma 2, and I'm operating on gamma 1 inverse gamma 1p. And the inside's a bit absurd, but it's absolutely necessary because I'm starting here. I'm starting in RD, which is what that thing is, right? So I'm taking the coordinates of P, feeding it to the inverse, and then pushing it to the other RD with gamma 2. Now, this notation here that I've written down for this is sort of your standard kind of calculus functional notation. It looks sort of like f of g of x. You may remember from the chain rule, when we studied the chain rule, you saw a lot of stuff like that. And you can also imagine it in a multivariable context as well, f of g of x. We don't like to use that notation. We don't like to use this notation at all. What we prefer to say is gamma 2, we like to give this function a name. We like to make this, we want to convert this to a function just of the coordinates of P. And we don't want to have it a function of a function. So we write it like this. We write gamma 2 composed with gamma 1 inverse of gamma 1 P. So I still have a function of a function in a sense, but what I'm really trying to say here is this is the coordinates of the point P. This thing is a function. It's just the name of a function, and it eats the coordinates of a point P. So my shorthand for the coordinates of the point P, I'm sort of stuck with the fact it's going to be gamma 1P, right? Because that is an ordered pair, right? A, B, up, it's a D-tuple ordered pair. So, but this is the notation that you want to become comfortable with, because you see it a lot in this study, and if you read a lot of books about it, you see them stringing together these things. Just think of this object as the function's name, and it's a good name because it tells you exactly what it does. It takes the argument, and the argument becomes the domain of this function. That thing will produce a result, which is this thing here, and then that result is fed as the domain of this, and the range of this ends up being the range of this function. So the domain, the function on the right of the composition symbol the function to the right, that's the domain of that function is the domain of the total composed function, and the range of the function on the left of the symbol is the range of the total composed function. But ultimately, this is a function from here to here, right? And we can take derivatives of that because it's a function of from RD to RD using the usual topology. So that's this thing here is called a transition function. And it's a transition from this chart, U1, to this chart, U2. It's a transition function. Now we're going to make the connection between transition functions and coordinate transformations soon, but it should already be evident. These are the coordinates of this point under this chart. This is the coordinate of this point under this chart. Obviously, the transition function takes the coordinates of the point under the first chart and gives you the coordinates under the second chart. It is a coordinate transformation. Well, I'll try to be a little bit more specific in a moment about how that might work. But there's obviously another one of these guys, right? There's one that goes the other way, like this. I'm just going around all of my writing already. And that one looks like, go back to green, gamma 2 inverse composed with gamma 1. Okay. I'm going to erase this guy here because he's just confusing. But I do want you to understand that you've seen composition functions before. Composition functions are totally obvious. It's just like regular old calculus composition, the function of a function. But now you have to just think about it in sort of one big lump term. That's all you got to do. And these transition functions are now RD to RD, so we can now start talking about taking their derivatives. And that's the big deal here. Because what do we know about these? First of all, let's be very clear. We've added nothing, right? This exists because we have a topological manifold. That exists because we have a topological manifold. The regions exist because we have a topological manifold. The images in RD exist because we have a topological manifold. These composition functions can be made simply because you have a topological manifold. You can always make them. This is continuous. This is continuous. These are all continuous. Therefore, the composition of two continuous functions is also continuous. So you're guaranteed, given that you have a topological manifold, you are guaranteed these transition functions are continuous. The way we say that is they are at least C0, right? That's the way we say continuous. They are at least C0. Now, they might, however, be better than C0. Better is obviously a subjective word, but if you like to take derivatives, then if all you are is C0, you're not very good, because you can't take if you're only continuous and not, if you're only C0 and you're not C1, that means you can't even take one derivative. C1 means the first derivative exists and is continuous. Likewise, C2 means the second derivative exists, and all the way up to CK, where k is some arbitrary number, the derivatives exist k times. We're interested in functions that are C infinity, that are infinitely differentiable. C infinity functions are called smooth. And we are interested in smooth functions. And our differentiable manifold is going to count as a differentiable manifold under our definition today. The way we're using it for our discussion here is if the transition functions are smooth, if they're infinitely differentiable as functions from RD to RD, which is what they are, they're functions from RD to RD. If they're infinitely differentiable, then you now have a differentiable manifold, which is better than the topological manifold. The topological manifold only demands that they are continuous. And it doesn't even demand that they're continuous. They will be continuous, because if you have a topological manifold, you will have transition functions and they will be continuous, right? But if they're more than continuous, if they're infinitely differentiable, then you have a differentiable manifold. All right, so that is sort of the core definition. Now, there are other definitions of differentiable manifolds that you will see if you study the literature on this. they're not very different, but they make different kinds of differentiable manifolds. They'll say you have a smooth differentiable manifold, right, if you meet the conditions we just talked about, a smooth DM. That is, the transition functions, gamma inverse composed with a gamma I inverse composed with gamma j, if that is an element of C infinity, I guess, the infinitely differentiable functions, let me not write it that way, but if this is infinitely differentiable, you have a smooth differentiable manifold. Otherwise, you'll have some CK differentiable manifold. A manifold it's a differentiable manifold, but the transition functions, they can only K of their derivatives exist. And then, of course, if you have a C0, you don't even have a DM, you have just a topological manifold. Okay, so that is the definition of a differentiable manifold. It's an extra condition. It's an extra condition on these functions, because being a topological space does not guarantee the differentiability of these things. For example, these things could be functions that have these weird cusps in it. So if you go to this spot where there's that cusp, it's continuous there, but the function, a derivative, doesn't exist there. And you can kind of imagine all sorts of transition functions that might have that property. So let's talk a little bit about coordinates now. This is important. We've defined a differentiable manifold. Now I want to talk a little bit about coordinates. Let me work in a quick example using our. I really like the example of the. I really love the example of the stereographic projection. I think that's a very good working example. So the manifold is in black, or actually in black is showing up in black is U1 gamma, the chart U1 gamma. Showing up in red, let's try to do a better line than that. Showing up in red is R2, the plane. And remember, if we look at this from the top, we have the infinite plane here, goes out infinity in all directions, and then the sphere is sort of sitting in the plane, cut in half, and the missing point is right there on the top of the sphere. So now we already know how to map functions from U1, gamma 1 onto the plane. I want to talk about the transition function. So remember, there's this other chart, right? The other chart has this point missing. Okay, so we have two different charts. We have U1, which is in black, and I guess we have U2, which is in green. Right, and of course they completely overlap, except they don't share one point each. So that's U2 gamma 2. So now I'm going to take a point in the plane, and that point in the plane, so this point in the plane will be, it'll be in the chart projection for gamma 1. So we want to create the transition function gamma 1 inverse compose gamma 2. Now gamma 1 was the black one, right? So the first thing I do is I execute gamma 1 inverse on this point. Now we can do this schematically, right? We just draw this line here, and that is the resulting point on the manifold of gamma 1 inverse of gamma 1 of P, if I call that point P. And then that would be gamma 1 of P. And this is an ordered pair. It's an ordered pair on R2. But I don't stop there. I then immediately execute gamma 2, and I find this point here. And that is gamma 2 of P. And of course, that's exactly what this function does. This function, however, skips the middleman and goes directly to there. And that's why it is a function from ordered pairs in R2, AB, to ordered pairs in R2, AB. Now in principle, this is actually a different R2 that it lands in, right? It's landing in a different R2. But to show the construction, we're going to double up the use of this R2 to represent both the range of gamma 1 and the range of gamma 2. So this is, and now we know that this is continuous with a continuous inverse, so this is a homeomorphism. This is a completely continuous and differentiable construction, so it's also a diffeomorphism. And it doesn't look like there's a lot of math in this. There should be a lot of math, but there isn't, the way I've drawn it. But you can make this rigorous with mathematics. You can define this line. You can determine what these intersections are. You can locate these points in terms of angles and stuff here. And if you did that, you would end up with these continuous functions that you can take derivatives of, depending on how you define your angles and how you arrange it trigonometrically or algebraically. However you arrange it, you can do this, and you will be able to come up with a real function here and take its derivatives. In fact, it's done in a lot of books, and I recommend you have a look. I really like the stereographic projection because it's very good to exemplify all these different things really well. Now, likewise, this would work for the coordinate functions as well. If I was just interested in the, if this was AB, if I was just interested in, say, x1 gamma inverse x1, the transition function of the first coordinate, right, I could do that, and I would have to take both coordinates because this transition function may depend on both x and y, or a and b. So, but this transition function is also going to be continuously differentiable. This needs to be sub gamma 1, sub gamma 2. All right. So the coordinate functions work in the same fashion. However, generally when you deal with charts, you're always talking about the full chart, the chart that takes an ordered d-tuple and gives an ordered d-tuple. When you want to break it down into just the individual coordinates, you kind of use these coordinate functions to do that. All right, so that's an example of how these transition functions might work. Okay, so the last concept, I want to cover a few things that you might run across if you read other material about manifolds. And the first is the notion of compatibility of charts. You'll usually see this depending on how mathematically detailed the material is. But it's sort of easiest to present by definition. And we'll say that I'll take two charts, U and gamma, and say V and phi. These two charts may or may not be compatible. So we're wondering, are they compatible? Well, the answer is yes if there's two possible ways of being yes. If U intersection V is the null set, they are compatible. So two charts that do not intersect are compatible. And I guess the way to think about that is if there is no place where they are overlapping, there's no place where they could be in conflict. And if they're never in conflict, well, they're compatible. If they do overlap, however, if U intersection V does not equal the null set, then we look at the transition functions between the chart maps. We look at gamma inverse composed with phi, and we look at phi inverse composed with gamma. And if these guys are smooth, if they're smooth, then they are compatible. So compatibility is a property of charts in a pairwise fashion. I take two charts and I ask, are these two charts compatible? Then, so that's the first part of this thing. Then the second thing is I look at an atlas. An atlas comes from a topological manifold, the set of all charts ui gamma I that make up the atlas. All members of the atlas in union, all the chart regions cover the topological space, which we've been calling X, topology of X, XTX. So we know that the union of all those charts certainly covers the topological space, And now the question is, are all of these charts compatible? Well, if it is a differentiable manifold, if X is a differentiable manifold, then of course yes, because, or if it's a smooth differentiable manifold, if I want to be particular, right? But we're talking about smooth differentiable manifolds. So if X is a smooth differentiable manifold, then by definition, every intersecting pair of charts has smooth transition functions. So one way to define a differentiable manifold is to say it's an atlas where all the charts are compatible, where compatible is defined this way. So you'll frequently see differentiable manifolds defined using this notion. Now, this notion leads to one kind of interesting question that you wouldn't necessarily think about using sort of the, if you didn't choose to go through this, which, by the way, is important. You really do need to know these concepts and these words. It's not like this is an optional section. It's just not the way I introduced it. I could have introduced the whole idea, defining compatible charts. I like the pictures, though. I like drawing the pictures with the lines a lot. But if we've got this question now, let's talk about another issue. What if I have another atlas? What if I have an atlas B, and I'll try to draw a fancy B here, like that, and it's an atlas, and it has its own charts. And it is an atlas on a differentiable manifold, and so we will say that these are all compatible as well. So all of these charts are compatible, and all of those charts are compatible. Now I take A and B, they're two different atlases, and I form the union. Remember, A and B are atlases, but atlases are sets. So sets can be unionized, and I do this, UI gamma I, VI phi I. And so now my question is, I have two questions. First, one's easy. Do I still have an atlas? Is this, which if I call that thing C, is that an atlas? And the answer, of course, is yes, it must be an atlas. And it's an atlas because this guy's an atlas and that guy's an atlas, so their union is going to be an atlas. The question, though, is C an atlas belonging to a differentiable manifold, right? That's a harder question. And the reason that's harder is because I know these guys are all compatible, because A is an atlas belonging to a smooth differentiable manifold. B is an atlas for the same topological space, but it may not be necessarily, but it's the same topological space. It is an atlas, they're all compatible, and it is a differentiable manifold. But my question now is, if I do this every single time, am I always guaranteed that these charts are going to be compatible with those charts? Because if they're not, then the union is not an atlas of a differentiable manifold. If I can find a single pair of charts in here that are not compatible, then I no longer have a differentiable manifold. And that means that X, Tx, and A is a differentiable manifold. X, Tx, and B is a differentiable manifold, but X, Tx, I should be scripting these, A union B, that is not a differentiable manifold. If these two of these charts, any two of these charts, are not compatible. So it turns out we're now leaving sort of the basic understanding and basic mathematics of manifolds, and we're actually asking a question that's a whole level deeper in the core mathematics of topology and differential geometry. It turns out that, I'll just cite the result as I understand it. Dimensions 1, 2, and 3, this is never a problem. If you have any topological space and you build an atlas, and that topological space is of dimension 1, 2, or 3, and I build a second atlas and I form the union, that union will always be another atlas, and if their atlases of a differentiable manifold, the union will also be completely compatible, and you'll always get a differentiable manifold. But once you get to dimension, well, then if you do 5, 6, and 7 on up to forever, in every dimension of 5 and higher, you're not guaranteed, you're no longer guaranteed that this union will also be a differentiable manifold. And in this sense, A and B are atlases that produce two different differential structures, and they call them differentiable structures. And in dimensions 5, 6, and 7 and higher, there are a finite number for any topological manifold in these dimensions. There are a finite number of different differentiable structures, and they're not the same. In dimension 4, it's even worse. There is an infinite number of them. Infinite number of differentiable structures. Now, it's more subtle than that. There's different types of topological manifolds, and some classes have an infinite number and others don't, and it's way beyond what we're here to talk about. The problem is when you read material from other books about this, they say if you've created yourself a maximal atlas, you have for every maximal atlas, there is a differentiable structure. And a maximal atlas is basically it's the union of all possible atlases such that the union remains completely compatible, right? So I take all the atlases I can, whereby the union of those atlases, everything is still compatible. Where if I make another atlas and I put it into the maximal atlas does not grow any bigger, and it remains completely compatible. All the charts are compatible. So obviously every differentiable structure has a maximal atlas. But if I try to add, say, in this example, if I tried to add B to the maximal atlas, if I tried to add B to the maximal atlas defined by the differential structure associated with A, it wouldn't work because they would be incompatible. There would be an incompatibility somewhere in that union. So the point is that when you read about this, books never discuss different types of differentiable structures because it's very, very advanced math. For example, you need a 7-dimensional sphere. It's called a Milnor sphere. A 7-dimensional Milnor sphere has multiple differentiable structures. I think the number's like 15. I'm not sure. But there's different differentiable structures for a Milnor sphere. So if you modeled reality using a 7-dimensional sphere, you better figure out which differentiable structure is the right one to model reality with. Fortunately, we're not going to be faced with that problem. But if you study this from other books, pay attention. Don't worry too much about this notion of the maximal atlas and differentiable structures, because I've never seen it actually come up in any study of general relativity. But it is important in the notion of understanding the mathematics of manifolds, and it's pretty deep stuff, and it's actually really interesting. But I've only scratched the surface of the subject, and it's fascinating. This whole thing about Milnor spheres and everything, and how to calculate the number of different differentiable structures is really, really interesting. And I don't doubt that it's relevant to physics, but it's not relevant to the physics we're interested in, which is your basic general relativity. All right, so enough about that, and let's just sort of wrap up. So we've talked about we've talked about the definition of a differentiable manifold, and to reiterate the final version, it's a topological space with an atlas, and all the charts in the atlas are compatible. And compatible, of course, is defined as the transition functions on all of these charts are differentiable. And they're smooth. They're smooth, which means they're infinitely differentiable. So we're only talking about smooth differentiable manifolds. Maybe I'll put an S there sometimes. We talked about that. We talked about coordinate systems and coordinate functions, right? We talked about coordinate functions. And That'll be important in our upcoming discussions about the tangent space. Okay, so that's it, and our next topic will be diffeomorphisms and tangent spaces.